I will not save, it's okay. And I will open a new case. And in this case, we start with natural flow. Okay, we start with natural flow. And later on, we will install simple gas lift with diluent injection. Okay, so let's start, and hopefully we can cover this faster. So I start with this section: oil, water, black oil, single stage separator, and other things I will maintain. But for sand control, now let's say we will install gravel pack. Okay, we will install gravel pack, natural flow, no artificial lift. So we can click done. All right, and then we go to the next section, the PVT. Solution GOR 800, oil gravity 37, and then the gas gravity 0.76, water salinity 23,000, and I don't have H2S, CO2, or nitrogen. And now I have laboratory data. So I want to perform PVT data matching. So how to do that? You open this match data section, and here you input the PVT data from laboratory. So for example, the temperature is 210, bubble point pressure 3500, and then you can follow me for the data. It's 4000, the gas oil ratio 800, oil formation volume factor 1.42 with oil viscosity 0.364. And then 3500, 800, and then 1.432, and then for this one 0.35. 3000 psi, 655, 1.352, 0.403. And then, for example, 2400, 500 gas oil ratio, and then 1.273 oil formation volume factor, and oil viscosity of 0.48. And then 1000, lastly, 190, 1.12, and 0.7205. Okay, so this is my laboratory data, and I want to perform PVT matching to match the laboratory data with the available PVT correlation from literature. So we can click match. All right, and here we have the data, the black boxes, and we have also several lines with different colors. They are the result from PVT correlation, PVT model. And you see, it's still, it's not match. And by clicking this one, match all, it's very easy. By clicking on this button, match all, I will try to match the data, the laboratory data, with all the available correlations. So click match all, click OK, and you see now they overlay almost perfectly. So which means that we have adjusted the parameters of the fluid model to get the best match. And to know which correlation is the best, we can check the parameters. Okay, so the best parameter, the best correlation will have parameter 1 closest to unity, closest to 1, and parameter 2 closest to 0. And the standard deviation, the lowest, the smallest standard deviation. So using this window, this result, you need to screen through. You need to check which correlation gives you the best matching. Glasso, Standing, Lassater, Vasquez-Bex, Petrosky et al., Almarhun, and De Ghetto et al. Which correlation gives you the best matching? And long story short, I will say that Glasso is the best for our current model, our current fluid. And for the viscosity modeling, I will say that Bill et al. Is the best. All right, the match one, because Glasso will have parameter 1 closest to 1, parameter 2 closest to 0, compared to other correlations. For example, parameter 2 it's 30, standing it's almost 200, Lasarter almost 300, so Glasso is the best. And for parameter 1, Glasso is closer to 1, I think, compared to Almarhun. But I'm sorry, I think Almarhun is even better, right? 1.0082, at least for bubble point pressure. But for solution GOR, Glasso is better than Almarhun. And for oil formation volume factor, again, Glasso is better than Almarhun. So again, overall, the best correlation is Glasso for bubble point pressure, solution GOR, and oil formation volume factor. Whereas for oil viscosity, you check, the best one is Beal et al. So click done, and you can check the plot. Click plot by temperature, and the first one, we touch this one, match data, let's say the gas oil ratio. So we have 5 points. This is our data, laboratory data. And then we select this one, gas oil ratio. You see they overlay almost perfectly. So this is currently for Glasso correlation. All right, so they overlay almost perfectly except on this interval. They do not match, but that's okay. Practically speaking, there is no correlation that will perfectly match our data. So from experience standpoint, I think this is already quite good. But you can also click finish and click plot all. And you can check bubble point. I think everything is okay. Gas oil ratio, here we have some problems with several correlations, but we can zoom in and check what is the best correlation closest to our data. And oil formation volume factor as well, oil viscosity, you can check which correlation is the closest to our data. And here, the red line is Beal et al. So again, Beal et al. Is the best for our viscosity correlation. So click done. All right. Again, you can click match all. And then you can again check plot by temperature. Yeah, and you can plot again. Okay. And so click done. Click done. Now there is a sign saying that PVT is matched. These green nodes. Okay. Okay, so click done. Now our PVT has been matched. PVT model has been matched with our data, so it's proper analysis. And you can see this sign as well, PVT is matched. And now we will enter the IPR data section. We will model the IPR using Darcy's equation. Okay, and for mechanical geometrical skin, we will use Caracas-Tarik equation. And for deviation partial penetration skin, I will select Chincho-Martin-Brown's correlation. Again, you need to familiarize yourself with Caracas-Tarik and Chincho correlation to get the skin factor. And reservoir temperature, for example, 4,800. Reservoir temperature, that's for reservoir pressure. Reservoir temperature is 210. And let's say the water cut is 0. Okay, with total GOR of 800 standard cubic feet per stock tank barrel. And now reservoir model. Reservoir permeability 50 millidarcies, thickness of the reservoir 100, drainage area 500 acres, DHC factor 31.6, so it's circular reservoir, radial reservoir. The shape factor, DHC factor is 31.6, but if you know the configuration, you can also calculate the DHC factor by opening this section. You input the length, width, distance to site D1, and distance to site D2 according to your, maybe you check the subsurface map, structure map, right? And you can input like this one. We have radial reservoir, so click done and click cancel. Let's say 31.6, that's for radial reservoir, and wellbore radius 0.354 in feet. And mechanical geometrical skin, because we have perforation, okay? So we need to input the damage, the skin factor calculation based on Caracas Tarik. So you can follow me, shot the reservoir permeability 50 millidarcies, shot density 8, perforation diameter 0.43, perforation length 9.2 inches. So the length of the perforation efficiency 90%, so it's 0.9. There is damage zone thickness, for example, 8 inches. So there will be damage zone if you perforate your well. Okay, you need to know that. With damage zone permeability 25. So it's half of the original permeability. And crush zone thickness, for example, 0.2 with crush zone permeability 12.5. So it's a quarter of the original reservoir permeability. Okay. And then shot facing 120 degrees, wellbore radius already, and vertical permeability 5 millidarcies. So it's 10% of the horizontal permeability. And then we need to input deviation and partial penetration skin. For example, deviation is 13 degrees, penetration 1. So we will perforate all the thickness of the reservoir, and the vertical permeability of 5 millidarcies. And now we input the sand control parameters. Okay, so you need to familiarize yourself with gravel pack properties. In this case, the gravel pack permeability, for example, 35,000 millidarcies, perforation diameter 0.43, shot density 8, gravel pack length, for example, 6 inches, perforation interval 100 feet, deviation 13, perforation efficiency 0.9, and beta factor method calculated. Phase choice, we will select multi-phase. Open the drop-down menu and select multi-phase. So far so good. We can just click calculate. And now we get the AOF, absolute open flow, 18,000 stock tank barrel per day, and beta factor calculated. So click plot results, rate and pressure, click done. So this is our IPR. And we get the calculated skin. Skin is 1.58, perforation skin is 1.60, deviation skin is minus. Yeah, deviation skin is minus, but it is not good. It's not big. It's just minus 0.016. So for example, again, if you have well test data, you can input here. For example, we have 2 well test data. Liquid rate of 4,000 stock tank barrel, for example, the pressure is 4,100, and the next one is at, for example, just for example, 10,000 stock tank barrel. The flowing bottom hole pressure is, for example, 2,850. You can click done, and you see the black boxes, our well test data, for example. But the most important thing is the IPR. So click finish, click done, done. So we have completed the IPR. And the next one, again, we need to input the well configuration. So tick deviation survey, downhole equipment, geothermal gradient, and average heat capacities. click edit. And now I will input the trajectory. Actually the same trajectory with the first case, hydraulic fracturing. Okay. And then lastly, this one. If you want to check the plot again, so click that plot button, finish, done. And then we need to provide downhole equipment. It's actually the same configuration as well. So it's tubing to 1000 feet or inches, default roughness, multiplier 1, and then of course we have subsurface safety valve with diameter of 3.72, and then tubing again down to 9000, and then the same tubing inside diameter and roughness. Lastly, the casing down to 9275 and inside diameter 6.4. So click done, and the overall heat transfer coefficient 8.64, and then the temperature 60 degrees Fahrenheit, 600 feet, 40 degrees Fahrenheit, and then at the reservoir level is 210. You can also plot the result. So it's like this. Finish, done. And lastly, the average heat capacities, we can maintain the default values. Click done, and we can check the summary. Summary in table. You can also click draw downhole. So it's our well schematic. So we have Christmas tree, and then tubing, subsurface safety valve, tubing again all the way down to 9000 feet, and then our casing. So click done, click done, click done. Just wait. Okay, so this is our well sketch. It's very easy. Now we just need to perform nodal analysis. Go to calculation, system IPR-VLP, and let's say the top node pressure, the wellhead pressure is 250 psig. And then for the vertical lift correlation, I will select petroleum experts, and then solution node, bottom node, and rate method, for example, again, automatic geometric. So click calculate. Okay, so this is the result, the nodal analysis for our original case, natural flow. Okay, natural flow of oil well. We get oil rate of 12,146 stock tank barrel per day. Okay, so this is the case where the water cut is 0. So for example, we already continuously produce this well, and the water cut increases. Okay, the water cut increases. So now we go to the last case. So this is the second case. It's natural flow. It's easy. So let's say the story is like this. Now the water cut increases to 54. Okay, 54%. So we need to change the water cut in IPR section from 0 to 54. Click done. Okay, and let's say after the water cut increases, now the salinity increases as well. Okay, the salinity of the water. Previously, the salinity is only 23,000, but right now it's 180,000 ppm. Okay, and with this high salinity, we fear there will be problem. Yeah, because maybe the salt will deposit and will create scaling maybe inside our tubing. the salt will deposit and it will block the wellbore because the salinity is too high. Right now it's 180. Okay, 180,000 ppm. So to solve that, we will dilute. We will make the liquid diluted. Okay, so we will inject diluent inside our wellbore. But if you inject diluent to make the salinity smaller, lower, to make the fluid more dilute, okay, you inject water. But of course, if you inject water, then your flow rate will be decreased because now it is heavier. The fluid will be heavier, and now the well will work harder to push the flow. That's why, in addition to diluent injection, we will also install gas lift, okay? So that the flow can will continue. Okay, so in one thing, we will inject diluent water to smaller down the salinity to avoid the salt precipitation, okay? But at the same time, we will also install gas lift to support the production. So now we click done. And now go to the option summary. Right now we are on the case 3. And now we change the artificial lift to diluent injection. Here, diluent injection. Okay. And that's for the method. The type is annular injection tubing production. Okay. So that's click done. And now we go to the PVT data. Here again, the salinity increases 180,000 ppm. And now we need to input diluent properties. Okay, the properties of our diluent. And the diluent type, we will use water. But now this water is with lower salinity. So it's fresher, more fresh than the reservoir fluid. The salinity is only 20,000 ppm. So 20,000 ppm, the diluent water will dilute the original water from the reservoir. Okay, again, this is to avoid salt precipitation that can block our pipe, that can block our tubing. So it's quite easy. We just need to provide diluent properties. Click done. All right, and the IPR will be the same. We just need to adjust the water cut to 54%. Okay, and click done. Now, because we install diluent injection, okay, there will be gas lift as well that we provide. So we need to, here, we add this section. Okay, and then the diluent depth is, diluent injection depth is at 9,000 feet. Okay, so that's the spot to inject the diluent water. And diluent injection rate, we start with 5,000 stock tank barrel per day. So click done. And we need to change this equipment data, downhole equipment. All right. So I think that's already good. Okay, cancel. So it's, let me check again. So tubing flow, and then producer, diluent injection. Oh, sorry. So here, annular injection, but plus gas lift. Yeah. And annular injection with gas lift. So now we will install gas lift as well. Click done. Let the system be ready now here. Okay, so now this is the spot of our diluent injection. And again, click this one. So the diluent injection depth is at 9,000 feet, diluent injection rate 5,000 stock tank barrel per day, and the gas lift gas gravity, injected gas gravity, for example, 0.7, no H2S, no CO2, no nitrogen. The GLR, gas liquid ratio, for example, 50, and gas lift depth is at 7,500. And later on, we will do optimization to get the best GLR and the best injection rate. So click done. Okay, and then here. So we have our injection gas lift injection depth here and diluent injection depth here. But again, we need to check downhole equipment. Okay, so far so good. There is no, oh, sorry, this one, casing inside diameter. Now we need to input casing inside diameter to calculate the annulus. So it's 6.4 and also 6.4 here. All right, so far so good. So click done. And we can check the summary. So there is error. Okay, let's go back to downhole equipment. Oh, here I forget to input the tubing outside diameter. So tubing OD is 4.8. Okay, so after providing the tubing outside diameter and casing inside diameter, Prosper will calculate the annulus. Click done and summary. This is summary in table and drawdown hole. So this is our well configuration. We have Christmas tree, tubing with inside diameter and outside diameter, and also the subsurface safety valve and tubing and injection point. Okay, and the casing as well. So click done, click done, click done. All right, now we are very ready to do the nodal analysis. So we go back to calculation, system IPRVLP, wellhead pressure 250 and water cut 54. And then total GOR is 800 and everything maintained as per default. And now we will create cases to get the best GLR, gas liquid ratio, and the diluent rate. So open the drop-down menu. We will do sensitivity analysis for diluent, in this one, salt diluent rate percent. So we will calculate the best ratio, the best percentage of the diluent. So it will be in range of 20% to 40%. So I will create 20, 25, 30, 35, and 40. Okay, and here we can click done, and then we can calculate. All right, so we have 5 cases of diluent percentage. This one for 20%, 25, 30, 35, and 40. And of course, if you increase the diluent rate, increase the diluent percentage, the flow rate will be smaller because now the fluid is heavier. Okay, heavier to be lifted. So the flow rate will be decreased. You can check the plot, system plot all cases. Done. So it's like this. You can maximize. All right. And go to replot here to get the original view. Click finish. Now, oh, by the way, you can check the sensitivity plot. So here, variables, get the liquid rate, click done here. So if you increase the diluent rate or increase the diluent rate percentage, your total liquid rate will decrease because now the fluid is heavier to be lifted. That's why we provide gas lift to make the fluid lighter. Okay, so click finish. Now in cases, we add GLR injected. This one, gas liquid ratio injected. And we have 10 cases from 0, 150, 300, 450, 600, 750, 900, 1050, 1200, and 1500. Click finish, click done. And then now we have 50 cases, right? But that's okay, Prosper is very fast. So click calculate. Let's see, now we combine gas lift injection with diluent rate injection. So we will dissolve the salt to make the fluid more dilute, but at the same time we inject gas lift to make the fluid lighter. Okay, so click OK. And now let's plot, system plot all cases. Done. Okay, so now we include all the 50 cases, sensitivity of gas liquid ratio, and the diluent rate percent. It's like this, but the most useful plot finish is sensitivity plot. So click this one. So it's pressure, salt diluent rate, change the variables to liquid rate. Okay, and x-axis variable GLR, gas liquid ratio injected. Click done. So it's optimization plot. The horizontal axis is gas liquid rate injected, gas liquid ratio injected. Vertical axis is liquid rate. And this one we have 5 cases of salt diluent percent. So now we will find which case will give us the highest liquid rate, or you can also change the variables to oil rate. Click done. So this one, the most important thing is I want to get the highest oil rate. And based on this optimization plot, it says that the best gas liquid ratio is around 800. Here, around 800. Or maybe this one. Okay, that's the best gas liquid ratio. And the best salt diluent percent is this one, this plot. So it is 20%. So it means the best configuration is to inject your gas with GLR of 850, maybe 850 standard cubic feet per stock tank barrel, and diluent rate percent of 20%. That will give you the highest oil rate and with dilute fluid.